there's this almost spooky phenomenon called quantum mechanics, where a thing can be in two states at the same time. And so the D-Wave quantum computer uses that strange property. But what the quantum computer actually does is it's able to compare many possible solutions at once. So if you imagine a regular computer, if it was searching for a solution, it would have to go through every possible solution one by one, see if that's a good fit. What the quantum computer does is it kind of lays all the solutions down and compares them all at the same time, so it can pick out the best one.
We put our quantum processor into something called the dilution refrigerator, which cools it down to 10 millikelvin, which is about 100 times colder than interstellar space, and essentially is the coldest place in the universe. The reason we go that cold is because of quantum information. So quantum information is extremely delicate, and because we still want our qubit to behave like an electron, so this still is a nice quantum mechanical thing, we have to really go to extreme measures to isolate it from the environment that it's in. And that's why we cool it down to such an extremely low temperature, because that temperature is strongly connected to our qubit because it's so big. It's going to cause it to jostle around, so we need it to be as low as possible. All of the information that's in our processor is basically, you can think of as magnetic spins. And so the information that's in our processor is going to be extremely sensitive to the magnetic environment it's in. And so just like we need to cool it down to an extremely low temperature, we have to also create an extremely low magnetic environment for the processor to sit in. That's about 50,000 times less than the ambient Earth's magnetic field. The shielded room is like the last layer of shielding for the fridge and ultimately the processor itself. Between the outside and the processor, there are about 15 layers of shielding, both magnetic and radiation shielding.
Imagine you have a series of peaks and valleys, like an actual physical landscape. And the objective is to find the lowest point in this very complex and jagged landscape. And now imagine that it's completely dark and all you've got is a flashlight. You might think that it's very difficult to find the lowest point because all you can do is look around you, and where the lowest point might be is far away. The advantage that you gain from doing things using quantum mechanics is that in a sense you get to traverse all of these paths simultaneously. So if you imagine a walker walking through this landscape, kind of taking a random path and then terminating after some point, you'll end up somewhere and you can backtrack and find the lowest point that you're at and raise your solution. Now imagine instead of just one, you had a large number, many more than the number of electrons in the universe, some big enormous number of paths. And from all of those paths you could pick the lowest point. The advantage that you get from using quantum computation is the advantage that you get this massive number of possible walkers through this landscape from which you can pick the best one, which gives you a significant speed up and increase in ultimate performance of your optimization procedure.